So here we'll talk about this actually for the same circuit as the previous page, and I'll try to explain what is the mesh analysis. And actually for mesh analysis, we try to consider the current of the mesh. So here for this circuit, you can see this is a loop, this is another loop, this is another loop. So we can consider we have two meshes for this circuit, known as this one. This is so-called I1. Okay, we can just ignore this I1, I2, I3 here. Okay, we consider this is I1. This is another one. This is another mesh called I2. So I1 and I2 are two meshes we defined. Actually, you can define it to be clockwise or counterclockwise. It's just up to you. Okay, so here we try to also define this node to be the ground. Okay, then we can try to write the mesh equation. So for the mesh equation, we actually use the KVL, and for the node equation, we use the KCL. So the KCL is about the voltage, and the KVL is about the current, so it's the other way around. Okay, so here let's see how we can write two equations for these two meshes with I1, I2 to be unknown. And then we can write two equations for these two unknown, and then we can solve it. Okay, so here, let's say for this mesh, actually we can just start from here. And then I1, and then going like this. So here we can see. Suppose I1 is going in this direction, and then we're going from this node to node A. Okay, so we will have a voltage drop. So it is actually I1 R1. And then from A to B, it is another voltage drop, E1. So we have a E1. So we just make all the voltage drop to be positive value. Just up to you, because as much as you don't make a mistake to the sign of all the terms, then you get the correct answer. Okay, so here we just assume voltage drop to be positive value. So from this node to this node is a voltage drop according to I1 in this direction. So I1 R1, and then going from here to here E1, and then going from here to here, we should consider the current to be I1 minus I2, because I1 is going in this direction. I1 is going in this direction. I2 is going in this direction. So the current going through I3 should be I1 minus I2. So here is still a voltage drop, and it should be I1 minus I2 times R3, and then going back to the point D, so equals 0. So this is the first mesh equation. And then for the second mesh equation, we're still going from here and then clockwise. So this current, I2 minus I1, and then times R3. And then from here to here, it is a voltage rise, so we should subtract E2 rather than adding it. Okay, so from here to here, I2 going this way, so plus I2 R2 equals 0. So this is the second mesh equation. So here we have the two unknown I1 and I2 and two equations. So we can actually solve it. So in this case, we can just collect the terms. So we have a R1 plus R3 I1 minus R3 I2 equals negative E1. and then we also have negative I1 R3 or R3 I1 R3 I1 plus R2 plus R3 I2 equals E2. Okay, so actually we can just solve it. Yeah, actually you can just multiply this one by multiply this one by R2 plus R3, and then multiply this one by R3, and then we add them together. Then you can eliminate I2 to get I1, and then you can plug it back to here, and then we get I1. Actually, this method and this method will give you the same solution. They should give you the same solution. Although here we try to solve I1 and I2 instead of finding VB. So for some circuit, using node analysis maybe easier. Some circuit using mesh analysis maybe easier. But most of the circuit using either way will be equally the same as difficult as each other. Okay, so here it also talks about the resistance in parallel. Okay, so I think here it uses the KCL, which means the node A, we consider the current going out, I1 plus I2 plus I3 should be I, the current going in this node. So we have I equals I1 plus I2 plus I3. And yeah, so here I1 is E over R1, or V over R1, and then I2 is V over R2, I3 is V over R3, like this. So we can just factor out V, yeah, so use V instead of E. Okay, so for the equivalent circuit, we try to equivalent this parallel resistance with this one. So for this one, we have I equals V over Req, which means that this one, the reciprocal of this one should be the same as this one, which means that 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so which means that for parallel resistance, we take the reciprocal of the resistance and sum them together, and take the reciprocal again to get the equivalent parallel resistance. Okay, so I suppose you should learn it before. So comparing the resistance and the capacitance, for series resistance we add them together, for parallel resistance we add the capacitance together. For parallel resistance and series capacitance, we take the reciprocal, add them together, and take the reciprocal again to get the equivalent parallel resistance or series resistance. So it is the other way around. And here actually, if it is for inductance, yes, still you can make it like L equivalent. For series, L equivalent should be summation of J from 1 to n, and then for parallel inductance, 1 over L equivalent equals summation J from 1 to n, 1 over Lj. Yeah. So when considering series or parallel, resistance and the inductance are the same thing, or the inductors. So here we have another sample problem. So it is very easy. So here we have a battery R1, R2, R3, R4. So the figure shows the multi-loop circuit containing one ideal battery and four resistance and with the following E values: R1, R2, R3, R4. What is the current through the battery? Okay, so here we can see R2 and R3 are in parallel. So we can just calculate R2 parallel R3. So it will be R2 times R3 over R2 plus R3. So we can just plug in the value 20 times 30 over 20 plus 30. So which is 600 over 50, which is 12 ohm. Okay, so R equivalent will be R1 plus R2 parallel R3 plus R4. So this one series with this one and then series with this one. Okay, so we have a 20 plus 12 plus 8. So this is 12, this is 20. So this is 40 ohm. 40 ohm. Okay, so what is the current going through? The current I should be E over Req. So E is 12 volts over 40 ohms, which is 0.38. Okay, so I think this one is quite easy. Okay, so next, what is the current I2 going through R2? Okay, so just now we already know that this current I is 0.38. It asks you what is the current I2 going through R2? I2. Okay, so here this is still 0.38. Okay, so here we can consider VBC. VBC will be I times R2 parallel R3, because you can consider this is R1, this is R2 parallel R3, this is R4, this is E. Okay, so when we consider VBC is nothing but I times R2 parallel R3. Okay, so in this case 0.3 times 12, which is 3.6 volt. So now we can consider I2 to be VBC over R2. So this is nothing but 3.6 over R2 is 20. So it is 1.88. Sorry, 0.18. Sorry, 0.188. And then what is the current I3 through R3? What I3? Yeah. Okay, so I3 will be VBC over R3. Okay, so 36 over R3 is 30. So this is 0.128. So when you add them together, it is perfectly 0.3. Okay, so next we have another sample problem. So this circuit will be a bit more complicated. We have 1, 2, 3 source, and then we have 1, 2, 3, 4, 5 resistance. Okay, so let's consider to use mesh analysis to solve this equation, to solve this circuit. So let us define, this is I1, this is I2, this is I2. Okay, so we go through these two mesh one by one. So for mesh 1, let us start from here. Let us start from here. Okay, so we go up, so it will be E1. E1 is the source, E1 is the source, and then it should equal to, so this one is going up and then going down should be on the other side. So it will be like, can just ignore this. Okay, or maybe here we can just let it there, and then we can just define this I2 to be counterclockwise like this. So this I2 will simply follow this direction. Okay, so here for this R1 we have I1 R1, and then from point A to here, we have this one to be I1, this one to be I1, this one to be I2. So this is I1 plus I2 times R2. And then for this one it is going down, so we have plus E2. And then from point B back to here, this is I1 R1. This is I1 R1 like this. Okay. So we can slightly rearrange the term. So we just move this term over and collect the term. So we have a E1 minus E2 equals, this is I1. So we have a 2I1 plus R2 times I1 plus R2 I2 like this. Okay, so this is the first equation. Call it equation 1, and then we have a mesh 2. Okay, so here we try to start from here, and then we going, yeah. So okay, so we're going in this direction, So here we have I2 R1. I2 R1 is a voltage drop, and then this, oh, both of them are E2. Okay, this is E2. This is a voltage. This voltage is going up, so we have a E2 on the left side, and then for the next one, I2 R1. So plus I2 R1, and then likewise, this one is I1 plus I2 times R2. I1 plus I2 times R2. And then for here, this is going down, so plus E2. So you can see that this E2 and this E2 cancel each other, and then we can collect the remaining terms. So we can see this is I1. So we have R2 I1 plus I1 I2 I2. So we have a 2R1 plus R2 times I2 equals 0. So we can call this one I2, and actually we can just plug in all the values. For equation 1, E1 is 3, E2 is 6, so we have a 3, equation 1 is a 3 minus 6 equal 2 times R1 is 2 times 2 plus 4 I1 plus 4 I2. And then for equation 2, we have 0 equals 4I1 plus 2 times 2 plus 4I2. So this is nothing but negative 3. Negative 3 equals 8I1 plus 4I2. And then here we have a 0 equals 4I1 plus 8I2. Okay, so we can just maybe multiply this one by 2 and then subtract this one. Then we will get multiply subtract by 2. So we have 8 times 2 is 16, minus 4 is 12. So we have the 12. We have a 12 I1 equals negative 6. So we have a I1 equals minus 0.58. This is the first answer. And then for the second answer, we just plug it back to maybe here, and then we have a 4 times negative 0.5 is negative 2. Negative 2 move to here. So 2 equals 8 I2. Then we have I2 equals 0.258. Like this. Okay, so we already find I1 and I2, and for I3, we already know I3 is I1 plus I2. So it is nothing but minus 0.5 plus 0.25, which is minus 0.258. So here we can use the mesh analysis to write two equations, and then we can find I1, I2, I3. If you would like to use node analysis, then I think you should define like this is VA, or maybe this is VA, this is VA, this is VB, and I think this is VC. Then I think you probably need to define 3 voltages and then Y3 equation to really solve this circuit using the node analysis. Then it will make things complicated, because you actually can define this is the ground node. So this is a independent node, and then this one VC plus E1. So you don't need to assume this voltage. And then for this one, this is ground, this is plus E2. So you don't need to define, but this one is independent. So you need to define this one. And for this one, this is ground, you need to define this one. And then this one is VB plus E2, so you don't need to define this one. So altogether, you need to define 3 voltages and then find Y3 node equations to get the same thing. Okay, so here we talk about the ammeter and the voltmeter. So ammeter is used to measure the current, and then the voltmeter is used to measure the voltage. Just very trivial. And actually, the ammeter should be in series with the current you need to measure, and the voltage should be in parallel with the voltage you need to measure. And the one point is the internal resistance of a current of the ammeter should be very small. Here is that the ammeter, the resistance RA of the ammeter should be much smaller than other resistance in the circuits, because it is like you connect a resistance here. So this is RA, and if it is large, then it will change the characteristic of the circuit, which is not good. So you should make this RA to be small enough so that though you make it in series with the current you want to measure, then it doesn't really change the characteristic. If this RA is large enough, then this I will change, all the other voltage will change also. But for the resistance of the voltage meter, this RV should be large, should be resistance of RV should be much larger than any other resistance. This one should be large. Otherwise, there will be current going in this the I going in this loop. Then it will change. Then it will change the characteristic, because this is I, this is I, this is IV. So you hope this one should be large. If this one is large, then IV will be very small. So there is barely no current going through this line, because if you don't connect this one, the circuit should be like the current I going through this R2 and R1. But if this RV is not large enough, then there will be some current going through it, then the characteristic of the circuit will change. Okay, so this is the RC circuit. This is the RC circuit. So actually we can use the KVL to write a ordinary differential equation for this circuit. So the idea is like here we have the battery, and then we have a resistance here, and then in series with a capacitor. So at the beginning, the circuit is connected. The switch is close to the node B, which means that there is no voltage charge on this capacitor. And at t equals 0, then the switch is short to the node A. Okay, so in this case, we can try to write an ordinary differential equation for this circuit. So actually, the circuit is like, so here we have a independent source, and then the circuit is like this, RC, and then this is the ground, and then when t equals 0, it will be like this. Okay, so for the initial condition, the VC0 should be 0 volt, because at the very beginning it connects to the ground. Then there will be no current. So because when t is smaller than 0, then it is like this. So this is a ground, and then there will be no current. So this node should also be ground. So in this case, VC0 should be 0 volt. Okay, so here we try to write the KVL using a KVL. So starting from this node and then go up to here, we have we have E. E is a constant. E is a constant. Okay, so here we try to consider this current I going in this way, and if you still remember, I already told you that the current going through the capacitor is C times dVc dt, if you still remember. Okay, so here we have R times I for the voltage drop of this resistor, and then the voltage drop here is VC, and actually this I should be C dVc dt. So we can just plug in this one here. So we will get RC dVc dt plus VC. So you can see here is a first order ODE with a constant coefficient. Okay, so we can try to slightly rearrange the term. So we have a dVc dt plus 1 over RC VC equals E over RC. Okay, so the first step is to solve for the homogeneous solution. So we change this one to S, and then plus 1 over RC, and then this one is 1 equals 0. So we get S equals negative 1 over RC. So in this case, VC, the complementary solution or the homogeneous solution, is A times exponential to negative T over RC. Okay, so we already get this one, this term. Okay, so for the particular solution, this is a constant, which means a zero order polynomial. So we also assume VCP to be another constant B. Okay, so we can just plug in this one into here. So for the first derivative, this is 0, and then the second term is a B over RC equals E over RC. So we will get B to be E, nothing special. So finally, we will get a complete solution to be VC equals the VCC plus VCP to be A exponential minus T over RC plus B. Okay, sorry, E. Should be E. Okay, and then we also have this initial condition. So we have a VC0 to be, if we put in 0 here, exponential to 0 is 1. So we have A plus E equals 0. So we will get A equals negative E. So we will get VCT to be E 1 minus exponential to minus T over RC. This is the voltage across this capacitor. And of course the I should be C dVc dt. So we take the derivative. This is a constant. Take the derivative will be 0. Take the derivative here will be exponential to minus T over RC. And then for the chain rule, we multiply it by 1 over RC, E over minus 1 over RC, and then we will cancel with this minus sign. So we have E over RC and then times C. So finally we will get E over R exponential to minus T over RC. So this is 2734 and also 2735. We actually can derive it by writing the ODE governing the circuit. Okay, actually we'll stop here. Okay, so maybe let's stop here today and then we'll continue next week.